All right, polynomial inequalities in two variables. So so we're all on the same page. One variable inequalities. Those solutions are graphed on the number line. Two variable inequalities. Now we look at solutions on the coordinate plane. And for lesson 3.1, some of you for those solutions were trying to graph them on the coordinate plane, but there was only one variable. So that's the difference for the graphs of the solutions. One variable, whether it's linear, absolute value, or a polynomial, is still on the number line. Then when we get two variables, that's when our solutions will be in the coordinate plane. Okay, so graphing inequalities in a coordinate plane. So sketch the graph for this inequality, and it's going to be exactly like we're already used to. All of our strategies for graphing, but a couple differences for the inequalities. So first we're going to graph the line, 2/3 x minus 5. Y-intercept of -5, slope of 2/3, up to right 3. And then you can go down to left 3. So now for an inequality, we have to see if it's a solid or a dotted line for the boundary. So since y can be greater than or equal to 2/3 x minus 5, we connect the points with the solid boundary line. Okay, and then we test a point not on the boundary. Easiest point to test is the origin. So if it's not on the graph of the function, then we can plug that in to test. And we plug that back into the original. So here's my original. If I replace both x and y with 0, I get 0 is bigger than or equal to -5. This is in fact a true statement. So when we shade the region that makes the inequality true, we obviously have to shade the region that includes that true statement. So we would shade above the line. And if you remember, obviously graphing lines, once we graph the line, we're finished. Inequalities on the coordinate plane, they have a whole region, a whole area of solutions. And that's why we have to find that region and shade the region that makes it true. All right, sketch the graph for 1 minus x squared. Okay, this is now a quadratic, so we have to go back to graphing quadratics. So we'll graph 1 minus x squared. Difference of perfect squares here. So my zeros are x equals plus or minus 1. Your vertex, remember that comes from negative b over 2a. Well, b is equal to 0 here, so my vertex would be the point 0, 1. So x-intercept at 1, -1. Vertex at 0, 1. It's a downward facing parabola because a is negative. All right, now when I look at the inequality, notice that I cannot equal 1 minus x squared. So when I graph it, I have to graph the quadratic. I graph that parabola with a dashed boundary line. Okay, so looking at the graph, 0, 0 is not on the graph of the function, so I can use that as my test point. All right, when I plug that back into the original, I get 0 is less than 1. This is in fact a true statement. So I shade the region that includes the point 0, 0. So that's going to be the region between inside that parabola. Okay, next one, y is less than 4. Okay, so think about what the graph of the line would be. Y is equal to 4. That's a horizontal line through y is equal to 4. From the original, y cannot equal 4, so this would be a a dotted boundary line. Now a couple things here. We can think about it, and if y is going to be all values less than 4, then that's going to be the region below the horizontal line. Okay, if you want to verify it with a test point, if we test the point 0, 0, well, I can only plug in 0 for y, and 0 is in fact less than 4. So again, we shade the region that includes the points that make the statement true. All right, absolute value of x plus 1 is greater than 3. Okay, I'm going to edit this inequality so that it is a 2-variable inequality, and it'll be a simple fix. We're going to look at absolute value of x plus 1 minus 3 is greater than y. Okay, so just subtract that 3, and then we're going to put greater than y. Okay, so now graphing absolute value. We know that the parent function for absolute value is our v, okay, with the vertex at the origin 0, 0. So now using our transformations, my excuse me, the vertex has a horizontal shift 1 left and down 3. Okay, so I take that point that was at 0, 0, and I go to the left 1 and down 3. Okay, absolute value is, it's greater than y, so I'm going to have a dashed boundary line, and the slope for graphing's sake is a positive 1. So that gives me my points. It's going to be positive 1 to the right of my vertex, and my slope would be negative 1 to the left of the vertex. Okay, so here's my graph. Okay, so fortunately, again, 0, 0 is not on the boundary, so we can use that as our test point. And I get absolute value of 1. So I get 1 minus 3 is negative 2. Is negative 2 greater than 0? That is a false statement. So now we have to shade the region that does not include 0, 0. Because of course the solution set is all points that make the statement true. So we're going to shade outside of the absolute value graph. Okay, one more, and then we'll be finished for these notes. All right, so if I look at the function as an equation, all right, greatest common factor of x squared, I take that out, I'm left with x plus 2. Finding the zeros of this polynomial, okay, the zeros are 0 and negative 2. 0 is going to be a bounce point on the graph. The degree is 3 with a positive lead coefficient. So my M behavior is going to be down up. All right, so I have negative 2 and 0. Fortunately for us, it is an equal to inequality, so the graph, the boundary line will be solid. So I start down, I cross through negative 2, I bounce at 0. All right, now here, 0, 0 is on the graph of the function. So I have to pick another point to plug in. And my suggestion to you is try and make it so that either x or y is a negative number. Okay, it just makes that much, it makes the substitution that much easier for you. So I'm going to test the point negative 1, 0. So here's my test point. Okay, so when I plug in negative 1, 0, I get 0 is less than or equal to negative 1 cubed plus 2 times negative 1 squared. Is 0 less than or equal to negative 1 plus 2? 0 less than or equal to 2. So after simplifying, this is a true statement. So I have to shade the region that includes that test point of -1, 0. So that'll be the region below the graph of my polynomial. Now notice, and I understand that our graph is slightly limited, but if I extended my function here, and then I continued to shade that in. So just wherever you're shading, make sure that the boundary, we would be able to see exactly what the boundary is. Okay, that's it for the video.